Where we get QFT and so on. Now we know that there are other ways to do this. Oh, well, of course, it's also a very, very well-known thing, starting from famous papers from 80s by Blötek, Nightingale, Affleck, Alcaraz, Martin, Luther, Tessin, Lukyanov, etc. There were many such papers where people identified low-line excitation of the spectrum of X-ray with the operator content of the QFT. Also, finite size correction, when this n goes to infinity, it also shows actually correspondence to the QFT if you look at this term here with some conformal charge C. The correspondence to the 6-vertex model looks like this. If we take R-matrix or L operator and enumerate one space by, for example, J and another one by M, and having in mind that we have many two-dimensional spaces of J, which we identify with so to say, spatial direction, and in vertical direction, we have what people sometimes call Matsubara. So in spatial direction, we have infinite dimensional space of states, it is HS, and in Matsubara it will be HM, which will be kept finite dimensional for a while with some finite n here. And we also imply that there are some inhomogeneity parameters which we call M, and the monodromy matrix is the object which acts in tensor product of this infinite dimensional space HS and finite dimensional space HM, which you see here. And in homogeneous case, we take all these tools to be equal to each other, like this. Okay, so the question is how do we get the local operators? And what do we understand by local operator? A local operator defined on this space HS will act non-trivially only on a finite segment of this space. So this is O, and we also multiply it with this Q to alpha S of 0, and S of 0 is, as we see, some semi-infinite sum from minus infinity to 0, and this is together with the scale, we call it quasi-local operator. Also, S of infinity, if k goes to infinity, it will give us the total spin. So this special operator will be called lattice primary field, in spite of the fact that it's not quite true, but still. And parameter alpha will be called disorder field.
So the operator is inserted at the origin. The operator is inserted at the origin, no?
At all. You take some place, yes.
Maybe it's
and call it origin. Yes. Yeah. So this is the partition function on cylinder. We actually wrap 6-vertex model onto the cylinder, and the cylinder is supposed to be infinite in this direction, which is for us kind of special direction, and this direction will be for us is Matsubara.
Sorry, is your tail going in horizontal direction? Yes.
What?
Tail
of operators.
Yeah, this process, yeah? So the circles correspond to disorder, the circles for semi-infinite. And this process correspond to magnetic field, which sometimes will be taken imaginary, pure imaginary. So the main object is actually what we call Matsubara expectation value, which is the ratio of traces with respect to these both spaces of this transfer matrix which act in terms of product of these two spaces with together with operator. So, and mathematically it looks like some functional which acts on the quasi-local operators. And these functionals will be called Z. So, now we come to this long story which we did together with Zimmer, Miller, Fedya, and Takeyama more than a decade ago. And the result of this long activity was construction of special creation operators, which we called T star, B star, C star, together with annihilation operators B and C. And they are constructed with the help of representation theory of quantum affine algebra EQs into head. And they act on the space W alpha, which is a direct sum of subspaces of quasi-local operators of some given spin S. So in fact, they have formal power series of spectral parameters squared -1 and have the block structure. So this T star doesn't change spin, B star C and C star B change spin by 1. In fact, so T star is bosonic, it generates commuting integrals of motion, and other operators are, it commutes with other operators, and they are, so to say, fermionic, or fermions, because they satisfy canonical anti-commutation relations, like this, with psi, some explicit function. And operators B and C annihilate this lattice primary field, like this. And space of states now is generated via multiple action of creation operators. T star, B star, C star on primary field. And in this way, we get fermionic equators. So actually, annihilation operators are singular at limit zeta squared to 1, while creation operators are regular. So we consider up to these factors Laurent series expansion with some modes BP and CP. And for creation operators, we have sort of Taylor expansion with modes BP star, CP star, and TP star. So there's a very important property, namely locality, which means that, for example, BP and CP acting on some operator X with a length smaller than P, they are killed, so to say, by this modes. And this creation operator modes enlarge the support by at most P. So in this sense, they are all partition function or relation to creation functions is as follows. If we consider creation functions which correspond to some quasi-local operator, or actually they are generated by two transcendental functions, rho and omega. And rho is, so to say, simple. It's related to one-point function. and omega is related to the nearest neighbor correlator, like this. So both functions depend on physical parameters like temperature, disorder, field, magnetic field. That's why we call them physical part. And in contrast to this, the basis is pure algebraic, so it is built using the presentation theory of quantum group, and that's why we call it algebraic part. So Zimmermill and Fedya around 2009 proved a rather important theorem that if we plug such product into the functional Zn, then the result will be quite simple, namely proportional to the determinant of Slater form of matrix with elements from this omega function actually. And then if we take expansions of the left-hand side row 1 and also of the right-hand side, then we can compare and find the result how the monomial of this creation modes act, and what will be the result if we plug it into the functional Dn. Okay, so one of my basic things in this talk will be the function omega and its properties. Some of them are actually new. And we define this omega in more general case, as Fedya said already, when we have two parameters actually, kappa prime, and we also can introduce different spin sectors corresponding to kappa and kappa prime, S and S prime, and define such objects. There are several equivalent definitions of omega, actually, again, in some particular cases. And first one was suggested by Zimmermill and further in the paper about the theorem. It was given in terms of deformed abelian integrals. Very nice formulation, which was extremely important for the proof of the theorem. But unfortunately, it was not very convenient for taking continuum limit. That's why we suggested with Hermann some other definition via solution of linear and nonlinear integral equations that come from thermodynamical description of the 6-vertex model. And let me also mention the third way, the function phi, which we suggest with Frank around 2012 actually. And in some cases, this third formulation will be more convenient. I will call it phi formulation. Okay. So let me concentrate on the second formulation, second description. In this case, this function omega has two parts. And first part is more complicated, it's omega tilde. Is proportional to some convolution of two functions, where f left is so to say simple function and g right is more complicated. It fulfills some linear integral equation. All definitions are here in the bottom. Yeah? So we have this kernel k alpha and this f left. Sometimes also need f right. And omega naught is kind of transcendental function of this kind with delta inverse. Delta is, so to say, difference derivative. So the convolution is defined with the following integral, where the measure dm is written here A is auxiliary function. I don't know who was the first one who introduced it. Andreas, maybe you.
Andreas introduced the integral equation, but Baxter used this already and called it P.
Already this auxiliary function. Yes. So this is proportional to the ratio of two functions. Yes, rho, as I said, is simple. It's just ratio of eigenvectors of transfer matrices at kappa prime and kappa. So Q is, as we know, a polynomial up to this multiplier with zeros at beta roots, and the beta roots, lambda I, in principle can be found from the Bertrand-Russell equation, which is this. Yeah. Contour gamma goes around all beta roots, and also zeta squared and psi squared must be inside the contour. Well, we can also define function omega plus by replacing psi by psi plus in all of our definitions. So actually, psi plus is even simpler than psi. So the difference is very simple. And we can rewrite actually both functions, omega tilde and omega tilde plus, by taking this zeta squared and psi squared out of the contour gamma. And if we do it, we come to the following formula. For omega tilde, where W is some explicit form, function, V is also explicit function, and this inverse U, U is some matrix, which is very typical in all this business. So up to some diagonal matrix, it is actually our kernel E alpha. And on the diagonal, we have 1 over mi, and mi are residues of the measure with respect to the beta roots. And similar can be done for the function omega plus tilde, so we do the replacements and come to the similar formula for omega tilde. Oh well. So what we see here is that these two functions, omega and omega plus, have following symmetries. Namely, if we interchange spectral parameters and take minus alpha instead of alpha, then we come to the same result. And for omega plus, we have to take instead of minus alpha, 2 minus alpha. Because of this simple formula, this would be psi plus. As we just seen from the Fedor's talk, actually both symmetries are important. They correspond to these reflections. And that's why the equation is when these both functions are equal to each other. And proposition tells us that it is so if alpha is this, when s prime is greater or equal s, or alpha is minus this, when s prime is less than or equal s.
Sorry, what was s and s prime?
S and S prime is just spin sectors. I can take them 0, for example, but in principle I can take them any spin sectors, U is, yes? It seems to me more convenient to show the statement using this third phi formulation. And this, here I have to be very, very short actually. What is phi? Phi is some function which has the following form with some phi tilde, and the following relation should be satisfied. That residue at all beta roots of this combination should be 0. And it can be checked that this expression for phi tilde solves this problem with the same matrix U that we had before. And then the functions omega and omega plus look actually as follows. They are proportional to the result of acting of two operators of difference type, which we call H capital. In one case, it's the act on phi, and in another case, the act on phi plus. H epsilon, zeta, this is given by this operator. Somehow it maybe resembles the Baxter's operator, but in fact it's not quite.
Hermann, sorry, you like showing already like second definition of omega.
This is third one.
Third one, but
yeah.
Like
they are all equivalent.
and they all satisfy that integral equation.
Sure.
And that integral equation is derived from beta ansatz.
No, it means that they're equivalent. Otherwise, they won't.
It's a separate equation. That integral equation could be derived via beta ansatz.
All that should be satisfied. So for phi plus, we get this instead of this with psi plus and u plus. And now I show why it is useful. If we take a difference of phi and phi plus, then we get something which is some factorized form in the right-hand side. Factorized, yes? And in fact, we can prove that in first case, the second factor appeared to be proportional, actually, to some function h, which is a ratio of two q functions, of q prime and q. This function h is a kernel of this operator h capital. That's why we get the two functions are equal to each other.
Question from my side.
Yeah.
You found a solution to this equation, I mean, a function with the necessary poles.
Yeah.
And you need asymptotics in order to have a unique solution. And do you control these asymptotics?
In some place, yes. We come to asymptotics. Yes. It's an important question. Actually, right now. It's about your question. So it's called normalization condition. So the claim is that for function omega plus and also for omega, in this case, yes, the limits when zeta goes to infinity, zeta goes to 0, or psi goes to infinity, or psi goes to 0, limits are 0. So, and this, of course, appeared first in paper by Zimmerman and Feder in 2009. But this is already something relatively new. This is kappa prime symmetry. I have to say, maybe I come to this point. We observe this property numerically, but now we proved it. And the statement is that the following relation holds. So this is our paper with Feder and the preparation. Work in progress. Okay. So maybe I have to skip the proof. If somebody is interested, we can discuss it. So now I come to application to quantum field theory. So what happens if we take continuum limit? Actually, our lattice becomes more and more dense. And you remember the scat corresponds to the local operator we plug in. And in this limit, it becomes to be concentrated at one point, actually. So this operator will be local in the sense of quantum field theory. So that's what we have in continuum limit, and more precisely what we do, we introduce space in A, and in such a way that product of n and spacing is 2 pi r. R is radius of cylinder, and this radius will be kept. It means that n goes to infinity, a goes to 0 in this way. So all tools are equal to each other. And then it's a very well-known result by Lieb that if magnetic field is 0, then the beta roots are distributed, right? Distributed with some distribution function, and this distribution function could be found explicitly. So actually, this Lieb distribution gives for n large this formula, and it gives us a clue how to rescale the spectral parameter. So if we rescale the spectral parameter like this, where C is fine-tuned constant, it's actually a famous formula by Alyosha and Molotchikov. And conjecture that we can accept here is that these both functions, rho and omega, have some limits, which we call rho scale and omega scale. Okay, and the same thing in principle can be done. I say in principle it's also conjecture that if we do it in special direction, then our creation operators T star, B star, and C star produce tau star, beta star, and gamma star. Now they depend on this rescaled spectral parameter lambda. And asymptotic expansion, when lambda goes to infinity, look as follows. And all these operators, these modes, they produce local operators in quantum field theory. In this case, in conformal field theory. So a few words about integrals of motion, found by Alexander Molotchikov in 1987. He found the following result that if one takes some certain densities, this h to n, actually these densities are all descendants of identity operator, and take the integral, multiplies with some local operator, or take this the integral around z, around w. Then what one gets is are integrals of motion. This is what Fede actually showed you. And the important property is that if we plug such integrals acting on some local field or between two states with conformal dimensions delta plus and delta minus, then the result will be proportional to the difference of integrals of motion applied to the states. Sometimes we call them dual. And look, if delta plus equal to delta minus, then E plus will be equal to I minus. And that's why it will be 0 in the right-hand side. So the Verma modules are spanned by the following elements. This is also kind of conjecture, if I understand. The Verma modules can be spanned by the following elements, but you take product of the local integrals of motion and product of Virasoro generators with even indices. So delta alpha is conformal dimension of this primary field phi alpha. And in case when delta plus is delta minus, actually the space is spanned by the even Virasoro generators, as I explained here. And it is equivalent to working on the quotient space. Quotient with respect module integrals of motion. So in these very famous papers by Bazanov, Okeanov, and Molotchikov, the following result was obtained for work rho, this expansion, and this C, J are constants that Fedya just actually told you. I will not write them again. And omega up to the square root is some double sum with respect to ij. Important is that this expansion goes only for odd indices here, and this mu in the denominator, this comes from the right way of rescaling. So the determined formula that we had in finite case looks in scale limit as follows. We are now in the right hand side, we have these functions. So we have to put this asymptotic expansions, and also in the left hand side we put asymptotic expansion for tau star, beta star, and gamma star, and then we can identify, yes, if we know a result in the right hand side.
So the factor 2 disappeared here. Did you?
I think we have rescaled. So technical problem is that actually we can proceed analytically so far for calculating this coefficients omega only for this case kappa equal to kappa prime and delta plus is delta minus, rho is 1. In this case, the Wiener-Hoff technique is applicable. And actually, we also do it in when kappa is large, the series with respect to inverse powers of kappa. Okay, so the conjecture is that if we take for the QFT 3-point function with some descendant of phi alpha is some polynomial with respect to Virasoro generators. On the right hand side, we should take our Zn that acts on this quasi-local fields and do this limit. And it appeared it works, and Fedya just demonstrated you the formula also for this disk. Maybe I will not repeat this. So there is several explicit identification modular integrals of motion of fermions and Virasoro generators. In all these cases, there is actually polynomial with some coefficients which are rational functions with respect to C and delta. But as Fedya said, starting from some level, they become complicated, unfortunately. Okay. So, how much time?
15 minutes.
15.
Not 20.
20. Ah, wait. So actually, the creation operators are not defined uniquely. So there is freedom in definition of this B star and C star, what we call gauge transform. So it looks like some simulated transform of B star and C star with some operator omega in exponential. And it's given by double integral with respect to C of product of C and B with some function omega prime. This omega prime can be in principle arbitrary function. And what happens if you do this, your original function omega will be shifted by omega prime. In fact, it is nothing but Bogoliubov transformation. So first choice is omega prime just 0, then we do nothing. And if we take naive limit n goes to infinity, and we don't rescale the beta rules, then what we get in this limit is very simple. It is just 1 if this local operator O is some power of translational operator tau, and 0 otherwise. And this looks very much like what happens in conformal field theory, because if you take one point function of primary field, it is either 0 or it is 1 for identity operator, right? In usual normalization. So this operator that we had, B star, C star, for target space V alpha no, have the following property when zeta goes to 0. What would be another choice of this gauging? Another choice would be if we take for omega prime minus omega 0. I hope you remember, maybe not everybody, what omega 0 was. And in this case, we get some new operators, B0 star, C0 star, which have the following property, because actually of this omega 0. And original omega has this limit, and remember, it was 0, yes, and in this limit zeta to 0 and zeta to infinity. But this, now this omega actually, the residual part will be exactly omega tilde, and this omega tilde will give us the following for B0 star and C0 star. So we get the following asymptotic, the following formula for the subspace W alpha 0, and the coefficients here, we call them screening operators, this B star screen J and C star screen J, they are non-local. So we, by this procedure, we create a non-local operator. Yes, and in scaling limit, again, we expect that we get this beta star screen and gamma star screen. And if rho is 1, then we have the following formula where we actually get already screen operator modes, expansion modes. And they are important, as you will see. So first of all, how do we construct primary field? As I said, in case kappa equal to kappa prime, we actually factor out the integrals of motion. So we consider, we get quotient space with the basis where we act by this B star, gamma star, product of these operators on the primary field. And in fact, what we do, we move inside the Hermann module, right? But we can also take the screen operators and extend our space. And let's call this extended space H alpha, and this quotient space belongs to this H alpha. So the important claim by Zimba, Mill, and Feyer around 2011 was that if we make some shift of alpha of the special form, then and take also quotient, it will also belong to this extended space H alpha. And this can be seen somehow. So in fact, if we act also by screen operators on phi alpha, note that what we do, we move between Hermann modules. And this is what we call shifted Hermann modules. So this is on operator, all definitions here. So let me come to Saint-Gordon now. Okay, Saint-Gordon action has this form, as you know, with some Kaupin constant beta, some scaled mass mu, and exponential field phi alpha has the same conformal, same scale dimension as the corresponding primary field in conformal field theory, with the same formula with alpha. So then relation to parameter nu that we had before is like this. Also P can be introduced. Yes, we are inside these two regions. And it's well known that Sine-Gordon model can be considered as integrable perturbation of conformal field theory, actually phi1, 3 to be precise, perturbation. On the other hand, it can be obtained as continuum limits again of the 6-vertex model. And what we should do, we replace homogeneous lattice by inhomogeneous one. So we introduce staggering with some parameter zeta naught here, and this zeta naught actually is something like inverse mass. So the way how we get the mass derivation. So the claim was that fermionic basis can be applied to Sine-Gordon model also. So what to do? So actually this B star and C star split into the pair of operator B plus minus star and C plus minus star, stemming from expansion series around zeta naught power plus 2 or minus 2 respectively. And the nearest neighbor correlator for B plus minus star and C plus minus star, it gives omega. And if we take plus minus minus plus, then we get omega tilde with different expansion for the asymptotic. Yes, so since Sine-Gordon model is perturbation, actually integral perturbation of QFT, then first of all, this exponential field in Sine-Gordon model should be identified with the tensor product of Hermann modules. Now we have to take also another chirality and take tensor product of V alpha for one chirality and V alpha bar for another one. And considering QFT and Sine-Gordon model as scaling limits of this homogeneous and inhomogeneous 6-vertex models respectively, one can actually expect that the action of local integrals of motion, this is I and I bar and also fermions, for QFT are in one-to-one correspondence with those for Sine-Gordon model. So we can identify them, so to say. Two chiralities emerge via the scaling. If we take B plus star and C plus star and do scaling, and then take asymptotic zeta to infinity, then we get local operators beta star and unlocal operators, non-local operators, beta star screening bar. Here we have gamma star and gamma bar star. For B minus, we should take after scaling zeta going to 0, and then we get another chirality actually, the opposite chirality. So identification of the shifted primary field can be got from that of the QFT. If we do it this way, maybe I just show you one simple example when M is 1. So in this case, you're up to some multiplier, you have a product of these four operators acting on this exponential field phi alpha. So simple examples would be in QFT case when delta plus equal to delta minus. The ratio of 3-point function with shifted alpha and unshifted alpha. And using this machinery, we would get this, and then it can be calculated, explicitly calculated, and on the other hand, it can be compared with the famous Dorn-Otto-Zamolodchikov formula. And the result appears to be the same. Another example, if one takes 1-point function of the Sine-Gordon model, And then we can also proceed for the case R to infinity. And this result can be compared with Lukyanov-Zamolodchikov formula for one-point function. And again, result matches. Oh well, so how many? 8. Maybe I could do that. So now I wish to look at asymptotics of our function omega in this scale limit, and it's more convenient to change variables, and it uses z for zeta in power p plus 1 and x psi in power p plus 1. And further, with slight abuse of notation, and apologies to Karl Weierstrass, because somehow I steal notation which is usual for Weierstrass function. It's actually related to my Latin problem. Everything what I do is raw. Nothing really happens. But maybe I will do it only once. So this curved rho is like this. Then also I introduce this psi, this curved kernel, and the function I am interested in is this capital omega, also this f alpha. And then to describe the function omega, we start with the Diels-de equation, which looks like this. And the deriving term, I know how to call it, this m, which is this constant, is nothing but soliton mass related to this original mass parameter mu through this also famous formula actually in the literature. And the kernel G is given by the following integral from our minus infinity to infinity. Okay, so for local rho, we have the following integral with some function L. And asymptotically, log rho, when z goes to infinity, the coefficients are proportional to difference of integrals of motion. This coefficients C was solved by Fedor, actually, and also some the soliton mass is here. And when Z goes to 0, then we get another gravity. I for integrals of motion for opposite gravity. So we need the so-called Drest resolvent, and we define it in 2 steps. So first we resolve the resolvent we call B resolvent, actually, which fulfills the following integral equation. And this convolution is given here. So this integral with rho in denominator. And then we define the Drest resolvent, which fulfills this integral equation, and convolution, this asterisk, is defined here. So in comparison with this convolution, we should also put this multiplier here. So we change the method. We can also introduce this f alpha capital, which is this f alpha small plus convolution of Drest resolvent and f alpha. And the function omega splits into 2 parts, omega 1 and omega 2, where omega 1 is expressed in terms of this f alpha, as you see here, and omega 2 is expressed in terms of u and this first convolution with u and alpha, f alpha, sorry, and u is some explicit function. U is given here. And the asymptotic for omega looks as follows. So in principle, we can consider 4 cases when log z goes to plus minus infinity, and also log x goes to plus minus infinity. And if this epsilon is the same, for example, plus infinity here, then we get coefficients omega that describe the same gravity, actually. And if we take opposite epsilon, then this coefficients omega will describe opposite gravity. So I already mentioned that several years ago, together with Fedya, actually mentioned this result in his talk. We also did some numerical computation of several coefficients omega, because still we cannot do it analytically at this stage. And at this stage we observed this kappa prime symmetry, actually. But we didn't understand at that time where does it come from. Now we have Okay, yes, what about shift of alpha? First of all, we use the following, this almost the same formula as before. And the following theorem connects omega with shift of alpha and omega without shift. And the residual part looks like this, where this psi capital is actually explicit function. It's written in terms of rho and also some cotangents, Tj. Yes, and actually in case when rho is 1, for example, there are some simplifications that happen. For example, this term is 0. And we come to the identity which was established in one of papers by Zubovic and Fedya, I think around 2011. And as I said, this equation was obtained for the case rho 1. But this is a more general case when rho is not 1, and we hope that it will be kind of useful. So now I come to conclusions, and so we saw that the function omega has many symmetries, in particular this kappa prime symmetry, which is satisfied in spite of the fact that these two parameters, namely kappa and kappa prime, enter in very different manner. And still we have symmetry of the function. It also has to do with the symmetry of 3-point function of in QFT, for example. Case. Probably the hope there exists an explicit symmetric description which might help us to solve this technical problem, which we call rho problem, and escape the condition kappa equal to kappa prime in order to involve contribution of the integrals of motion. And Fedya gave some results in this, explained some results in this direction using this two reflection releases. And as we saw, this omega in the special case is symmetric with respect to reflection sigma 1, which is this alpha to 2 minus alpha, which is also connected with natural symmetry with QFT. Yes, because of this formula for conformal dimension. I did not discuss the second reflection, alpha 2 minus alpha, which originates from the Sine-Gordon model, but Fedya discussed it. So the idea was promoted by Negra and Fedya, and it helped us to incorporate several integrals of motion for a few particular cases, what Fedya explained in his talk. And this last relation with shift of alpha, I hope should be helpful in further understanding of the shifted Virasoro modules. And in particular, there are plenty of identities, different identities discovered by Zimmerman and Smirnov in this context. And I hope it will be possible to realize how these identities can be shown. What I didn't discuss, null vectors, what Fedor discussed. I also didn't discuss such things like conformal blocks, because also they are vector results. Okay, thank you.
Other questions? I have one.
So in the CFT case, you mentioned that this expectation value was related to the Liouville 3-point functions.
Yes, right.
So my question is not about the massive case. Can you make similar statements?
Yeah, massive you mean Saint-Gordon?
Yeah, but yes, I mean.
Yeah, that's what I...
So, but do you have an analytic matching of, say, the small volume expectation value with the...
Only numerics. Numerics is fine.
But there's some support, some support for me.
I have one or two questions. In the continuum limit, the omega function, I mean, would it degenerate to something trivial? Or?
It depends on the limit you take. If you don't rescale spectral parameters, then it does.
I see.
That's what I showed.
Okay.
It is one when you take translations or some power of translation.
I see. And
Zero other, yeah.
I mean, usually when we think of continuum limits of these correlation function formulas, which we have as many products of omegas and
Yes.
then, well, the trouble is if you want to keep finite distance and we do continuum limit, then on the letters we have to increase the distance, and then the formulas get, so to say, unmanageable.
Yeah.
Does
This conjecture that this conjecture is also supported through many things. That on the right-hand side you get again determinant of scaling of function in the scaling.
Yeah.
This can be done separately. So you consider the scaling limit of omega, you consider the scaling limit of rho, and describe them as I did. And then you have to take the asymptotic expansion in both sides.
Okay.
This
Maybe we'll continue a bit later.
Sure.
Is there another question?
You mentioned that you can work with massive Saint-Gordon, yes? There are some mapping from, as far as I remember, from massive Saint-Gordon to Liebdiniger. There are some mapping from massive Saint-Gordon to Liebdiniger. As far as
It's Sinch-Gordon.
Sinch-Gordon, not Saint-Gordon.
not from Sinch, and you cannot work with Sinch.
I think we can. We can. But it was a little bit different. So please ask Fedor. Fedor knows more. They had some paper with Stefano Negra about Sinch-Gordon.
And with Zoltan also. You can ask Zoltan as well.
Okay, let us thank Hermann again.